All right. Everyone can hear me, right? So today we are going to talk about partial derivative more. So let's talk about the thing that we stopped last time. So last time I told you that the today lecture we are going to define two-dimensional derivatives. So it means we wanna get into how to define derivatives in two dimension. So last time I told you that here you have uh, the graph of fx. This is in one dimension. So if you graph this one fx, so you're gonna get this curve. Well, basically in calculus 1, you can define derivative by using limits. So if you take limit of fx plus h minus fx over h here, this is a formal definition of limits. You call, formal definition of derivative. You call this thing in Cal 1 derivative, and you give it notation f prime x. This is the derivative in calculus 1. Well, you can see that in calculus 1, you don't use definition, the formal definition a lot. What you use a lot when you calculate, in practice, it's gonna be the formula. So basically, we are trying to develop the definition into dimension in the same way as in calculus 1. So we can keep the formula. What we want is we want to keep the formula so we can use it again into dimension. So you're going to see in a minute how we define derivative into dimension. The way we define, we're going to force it to be simple so we can use the formula that we learned in Cal 1. So it's beneficial for us to use the formula that we learned already. So as I told you last time that in two dimension, we're going to extend the idea into two ways to define derivatives. So because you have x, y, so you need to specify which variable you are going to take derivative with respect to. So last time I told you that we're gonna have the derivative with respect to x and the derivative with respect to y. Okay, so let's get to that definition. Okay, so we're gonna move to the next slide. Okay, let's talk about the definition of um, derivative for a function of two variables. So let's suppose that you have fxy. Okay, fxy. How would you define the derivative? So again, we're gonna use the idea that, well, let's start by fix one variable. So if you want to do the partial derivative with respect to x, you have to fix y to be constant. So we're gonna let's start by fix y equal to b. So you're gonna fix y to be constant. So where b is a constant. So once you fix y equal to constant, what you have is, let's call this thing c. Then we have, your function gonna be f, right? Well, 1 second, c equal to f x b. So if you let y equal to b, then you replace b here. So the function here that you have, the function that I circle here, this is no longer two variables. This is going to be just a single variable function, right? This thing come back to one variable function. Because you already fixed b to be constant. Well, once you have a function of one variable, you can use the same definition as you did in calculus 1. So now we're gonna define this to be limit where h go to 0. For f, this time we're gonna fix b. We're gonna fix b, right? Well, let's keep b fixed to be constant, and then you move your x here. So you can move, let's say you're gonna say that it's going to be your a, b, the point a, b here. And this is going to be a plus h over h, okay? Well, basically you do nothing other than using one variable function, but you fix b to be constant. So basically you will this thing to be a function in a single variable, and then you keep b fixed. You can see that b does not change at all. So b going to be the same because you fix b to be constant. And then what you move here is going to be your x variable. So you move from a to a plus h. So it means you are looking for the change in the x direction, but the y you keep it fixed. And this is a definition of derivative in two dimensions. So we're gonna call this thing to be the derivative of f with respect to x at the point AB. This is how you define derivative in two dimensions. Does it make sense? But as I told you that when we do the calculation, we are not going to use the definition. Well, if the question asks you to do the definition, you have to. But if the question does not specify the method that you have to do, you can do the formula using the formula that you use in calculus 1. It's totally fine. So this is the formal definition of partial derivative with respect to x. Well, usually we don't use the formal definition. We're gonna use the formula. Well, the formula works because you can see that the idea that we define, we use the same way, the same definition as in calculus 1. We just fix b first, and this gonna come back to a single variable function. Well, with the same idea, you can define f subscript y as well. This is going to be the derivative, partial derivative with respect to y. So the idea going to be the same thing, that you keep a fixed and then you increase your b. So it's going to be, you start from the point and then you keep the x direction fixed, which means you keep x equal to a to be a constant fixed, and then you just move your b to b plus h. Okay, this is going to be the partial derivative with respect to y. For those of you who think that this is so much abstract, that's fine. This is so much abstract. This is the way we define derivative. But as long as you can do the example and you can calculate it, that's fine. Because the goal for this class is that we want to make sure that you can do the calculation first. For the theory part here, if you are interested, you can take more class into deeper mathematics idea, some kind of real analysis class, or well, because you are BBTECH student, you don't have to take that class. But if you are interested in, on the third year or the fourth year, maybe you can find the elective course to do the real analysis or something that looking into the proof of this thing, so you can understand the theory behind it more. But for calculus, we're gonna make sure that everyone can do the calculation. That's our goal. But I have to say the formal definition too, because some of you may wonder that what partial derivative is in terms of, oh, this is the definition, okay? All right, so let's discuss about the notation of partial derivative here. So we have notations that we're going to use. So for partial derivative with respect to x, so what are we going to use? Is we can use f subscript x ab here. This is one notation that you can use. Or you can use derivative of f with respect to x ab here. Well, this is the same notation as you did in Cal 1, but the different thing is you make this thing to be more curvy. This is called curl. This notation is curl. In math, we read it as a curl. So sometimes you're gonna see people read this thing curl f by curl x. That's fine. So it's, this is the same idea as what you did in Cal 1. You use df by dx. If you are talking about one dimension, you're going to use the standard d. So it's going to be d with straight d. But if you talking about 2 dimension, people are going to use curve. So make it more curvy, so you know that this is partial derivative. This is in 2 dimension. Make sense? Well, in all textbook, you could see something like D1FAB. This is also valid. So in some textbooks, but you don't see it a lot in the real world now. So this is also partial derivative of f with respect to x. Or sometimes you can see if your function c equal to fxy. Sometimes you're going to see people use curl c by curl x, given that evaluate at xy equal to ab. This is fine too. So it means you are trying to do the partial derivative with respect to x, and then you evaluate at ab. These are notation that mean the same thing, partial derivative with respect to x. But the one that you're gonna see a lot gonna be the first 2 here. You're gonna see a lot because this is more common and people use it more. So for partial derivative with respect to y, you can feel the same way. Just change the notation from x to y. Right? It's gonna be f subscript y ab here. This is one notation. Or you can have curl f by curl y. This is ab. Okay, this is fine too. Or you have d subscript 2 fab. This is also partial derivative with respect to y. Or you could have curl c by curl y, given that xy, evaluate at xy equal to ab. So I get confused a lot with probability. When I teach probability, I use the this notation for given. All right, so evaluate at xy equal to ab. Sounds good? Well, this is a notation. So again, the notation that I highlight in yellow, this is the one that you're gonna see a lot. Okay. So last time we talked about how to get the partial derivative already. So keep in mind that when you do it, when you do the partial derivative, so it's gonna be partial derivative with respect to x and partial derivative with respect to y. So when you do partial derivative with respect to x, you keep y to be constant, because from the definition, you start from fixed y to be constant, so you can get a single variable, which means when you do it in calculation, in the real calculation, you have to keep y to be constant. So keep y to be constant, and you just differentiate with respect to x. You can see that from last class, I told you that when you look at the function, trying to look at y to be just some numbers. So it makes the world easier for you. So like for x to the 4th power, you're gonna differentiate and you get 4x squared, because formula, simple formula, right? From Cal 1. 3x squared y, you look at 3 and y to be your constant. So you do not need to differentiate 3 and y. It is a constant. And then x squared is only your variable now. So you differentiate x squared, you get 2x. That constant 3 and y you pull out. So you get 3y here. You're going to do the same idea here, like every time until you get familiar with this technique. Okay. Today we're going to practice more on partial derivative. Let's get to more example. Okay. Any questions so far? Well, student, please check in the chat now. 28 students here. I want to see who come in. So if you are listening to me now, type something in the chat, your name or something, so I know you are here. All right, so example 19. Thank you, everyone. All right, well, we're gonna look at example 19 here. All right, so suppose that fxy equal to this function. We want to evaluate partial derivative with respect to x at the point 2, 1 here. So how will you do it? So again, if you see here, f subscript x, it means you have to take the partial derivative with respect to x, which means you have to view y as a constant. Does it make sense? You have to treat y as a constant. All right, and then once you evaluate derivative with partial derivative with respect to x, you plug in number 2 and 1 at the end. So you're gonna get the answer. Does it make sense? So we're gonna look at that. So first we have fxy equal to x squared plus 2y squared square root x squared minus y squared. And then now you're gonna treat y as a constant. So you can well here let's try to look at the function f first. So 2y squared constant, right? And then minus y squared, this is also constant. So your variable here is just x and x. So there's no way that you can differentiate without using the product rule, right? Because you have this thing and this thing, you have two things multiplied together. Well, in calculus 1, when you have two things multiplied together, you always use the product rule, right? In Cal 1, if I ask you to differentiate x squared sine x, remember everyone, in Cal 1, if you want to differentiate this thing, what would you do? So you're gonna do, okay, keep the front one x squared, and then you differentiate the latter one sine x, right? And then plus sine x, and then you differentiate x squared. This is what you do in Cal 1, right? When you see the product. Because you learn in Cal 1 that differentiate uv. This is going to be u dv plus b du, right? This is in Cal 1. So again, you can treat this thing as your u. You can treat this thing as your v. And then we can apply the product rule, okay? So I'm gonna say this is my u, and this is my v. So I use different colors so you can see the difference. So we're gonna take the partial derivative with respect to x of this function. So first of all, I'm gonna keep x squared plus 2y squared here. And then we're gonna differentiate the green term here. And then plus, I keep the green term to be outside the operator. And then we have partial derivative with respect to x of this function. Is that okay for you? So I'm trying to go slow here. So you have the green term and the light blue term here. So you can see this is my u, this is my v, and then you get u dv plus v du as in calculus 1. This is how you use the product rule, right? So the thing that you already took it outside the partial derivative, like this term and this term, they are fine already, so you don't have to touch it. So all you need is you need to evaluate something inside here. So let's go. So this is x squared plus 2y squared. Keep it outside, you don't have to do it. Well, for this one, if you feel like this is way too hard to do it, so you can do x squared minus y squared to the 1/2 first. You know, just simplify first because you are a beginner. Maybe it's easier when you, you know, change the form of square root to something raised to the 1/2. And then this is going to be square root x squared minus y squared. Well, on the last term, this is easy, right? Because you have x squared plus y squared. Okay, you differentiate with respect to x. What would you get here? So you differentiate x squared, you get 2x. Differentiate 2y squared, but y is constant. So it's going to be 0. Sounds good? So at the end here, you get 2x plus 0. Because the last term 2y squared, you treat it as a constant. So it's going to be 0. So x squared is not a constant, so it's 2x. Well, this thing is outside partial derivative already, so it's keep it there. Okay, so this term is good, this term is good, this term is good. So you only need this one. Okay, let's do it. So x squared plus 2y squared. So differentiate this thing if you remember from Cal. So if you have u to the n, right, you're gonna have nu to the n minus 1. It's like derivative. basic derivative. But because of the chain rule, you're going to have du by dx as well. Because if your inner function is not just x, you need to differentiate inner function. Remember when you learned with Ajahn Ratinan last time, last semester? So here you're going to have x squared minus y squared to the 1/2. So you get 1/2 x squared minus y squared raised to the negative 1/2. Make sense? And then you differentiate with respect to x of the inner function. Well, this is a little bit complicated, but not that much. So you can see that, well, I am now focusing on the term that I boxed here. Everyone look at it. So you move 1/2 down because of the chain rule. You have the inner function raised to the 1/2. So you have 1/2, the inner function. Here, this is 1/2 minus 1. So it's negative 1/2, right? And then inner function is here. And then, well, you simplify a little bit more, x squared minus 2y squared. And then this is going to be 1 over 2. And then here going to be 1 over square root x squared minus y squared, right? And then differentiate x squared minus y squared here. Simple. So you have 2x minus 0. Again, remember that y is constant. And then you have plus 2x square root x squared minus y squared. Well, this is done already. This is the answer for partial derivative with respect to x at the point xy. General partial derivative with respect to x. The question asks you to plug in fx at 2, 1. So you plug in number 2 and then 1 and then 1/2 and then square root 2 square minus 1 square and then 2 and then 1 and then plug 2 and square root 2 square minus 1 square. If you calculate everything, you're gonna get the answer. So 2 cancel 2 here, and that is the first term is 4 plus 2 is 6, right? This term is 1 over square root 3, and the last term is 4 times square root 3. Wow, a bit crazy, you know. And then that is 6 times square root 3 over 3 plus 4 times square root 3, and that is 6 square root 3. Is that right? So let me look at my notes today. Going for am I right? That is, well, that is not my answer. That is not 6. Hold on. 4, 5, 6. Okay, I think I did it right. Okay, 2x is not 2. Sorry, that's why. This is 4. This is 4, and that is going to be 2. So you need 2 here as well. So let me fix my answer first, and that is 12. Sorry. That is 12 over square root 3 plus 4 over square root 3, and that is 12 square root 3 over 3 plus 4 square root 3, and that is 8 square root 3. All right, good. Now, sorry, I messed up here because this is 2x, so you have to plug in 2, and then you get 4 over there. All right, it's not easy, not that hard. All right, thank you, Siri. Viranya, who texts me in the chat. Yes, that is why I messed up. Thank you. Well, you are a good student. All right, so well, some of you, well, if you understand this example, give me a thumbs up, or any reaction, so I know how many people understand it. All right, so, well, because some of you text me in the chat that you need more explanation. So I think for those of you who cannot catch up with this example, I think your problem is about this 2 line, right? So it's gonna take you more time to understand if you have less experience in calculus 1. So here I use the product rule for the first time. Here I use the product rule, and then once I use the product rule here, So this step to this step, I have done nothing other than simplify this thing to that. And this thing, I take partial derivative, so get that. Well, this step is a little bit tough for those of you who forgot calculus 1 already. So you have to recover that thing again. So it's gonna be like you have the chain rule. Inner function raised to the 1/2. So you get 1/2 inner function raised to the negative 1/2, and then differentiate inner function. If you feel like this is way too hard, or if you do not understand, you cannot follow, it is because you already forgot the chain rule in Cal 1. Like remember in Cal 1 when you differentiate x, let's suppose you want to differentiate sine x to the 1 over, let's say 1/5. What would you do in Cal 1? So you're gonna do 1/2, and then you keep sine x, and then you do 1/2 minus 1, right? And then Ajahn Latinan gonna say, oh, you have to differentiate inner function as well. So which means you have to multiply, differentiate sine x. Because this is the inner function, this is not just x. Well, we do the same thing here. We have x squared minus y squared to the 1/2. So that means I have 1/2 and then that inner function. And then here gonna be 1/2 minus 1. And then I have to keep the inner thing to differentiate at the end. Makes sense? And this to this, I just simplify it. Simplify that one. And here I differentiate using partial derivative. Sounds good? All right, so well, take a deep breath because we have more examples. So you're gonna keep doing this for 2 weeks. This week and next week, we're gonna keep doing this thing. So hopefully after next week, you're gonna get better with partial derivative. Sounds good? All right, let's take more step to example 20. Well, I think I go pretty slow, so I'm gonna increase my pace a little bit now. So example 20. So let's suppose we have fxy equal to x squared times y times e to the xy. Looks complicated because you have so many xy together. All right, so this time I want you to evaluate curl f by curl y at the point 1, 1. So again, you need to differentiate with respect to y. That means you have to keep x constant. So you're gonna keep, well, here it means with respect to y. It means you have to keep x constant. Every time you do the partial derivative, think this way first. Well, it's gonna be useful because when you do the integration, you're gonna do the same thing. Well, after Songkran, when you do integrate with respect to x, you're gonna keep y constant. Integrate with respect to y, you're gonna keep x constant. Well, the same idea gonna carry to integration as well. So you need to learn from now. Now you need to learn derivative first, because if you are good with derivative, you're gonna do good again in integration because they use the same concept. Okay, well, this time, well, let's look at the function fxy equal to x squared times y times e to the xy, okay? A little bit tough, but now you will x as a constant, so you don't have to worry about x. So what is your variable here? You have y. Look at the one that I highlight, and you have y. Well, again, no way you can avoid product rule, because you're gonna have this thing y and e to the xy. It is a product. Well, we're gonna differentiate. Well, let's try to differentiate f with respect to y first at any point xy. So it's gonna be something like, oh, well, you don't have to differentiate x squared, right? Keep it. Well, x squared, just pull it out first. X squared just constant. Go away. So x squared just outside the bracket now. So now you need this term, y to the e to the xy, okay? So keep the font fixed, and then keep y, and then you differentiate the function with respect to y. This is the function with respect to y. Well, the function, well, this is my u, this is my v. So keep u, you differentiate v. And then next, keep v, you differentiate u. Well, looks pretty easy and simple, more than what we thought at first time, right? And then here you have x squared, and then you have y. Well, all right, so this thing again, you have to use the chain rule now, everyone. So e to the xy, it's like e to the sine x, for example. When you differentiate in Cal 1, you're gonna, oh, differentiate e, you get the same thing, but we have the inner function, so you have to differentiate sine, you get cosine. Well, the same thing here, you have to keep e to the xy. Well, you get e to the xy, fine, but inner function ครับ xy gonna come multiply to the n as well. This is because of the chain rule. All right, plus e to the xy, and this one is 1. Good, because differentiate y with respect to y, 1. All right, and then that is x squared, and then y, e to the xy, and then that term differentiate xy with respect to y. What would you get? Differentiate y, xy with respect to y. What would you get? Answer me in the chat. Differentiate xy with respect to y. X. Good. Thank you. Because x, and then e to xy. Well, you are done with the general form, right? Good. And then now you plug in that at the point 1, 1. Okay. So let's plug in 1, 1, e to the 1 times 1 plus e to the 1. Wow. It's actually 2e, right? At the answer. Because you're going to get e plus e, which is 2e. Well, this is easy, you know? Okay. Well, hopefully you feel like you get more familiar, right? After 2 examples, you feel like, okay, be confident about your, be confident about your skill of derivative, because this is what we're going to use again and again. All right, so, well, let's talk about example 21. So some of you say that, Ajahn, what if I don't want to use the formula? If you don't want to use the formula, you can use definition, but it's a little bit harder. So I'm going to show you how to do it by using the definition. Okay, example 21 here, given that the function is here. Everyone see that if you use the formula, you differentiate f with respect to x. Well, keep y constant. So it's going to be 1 plus 0. It's 1. You can get the answer like in few seconds. Or if you use the formula, differentiate f with respect to y, and then it's going to be 0 plus 2y, and that is 2y. Well, your answer is going to be quick and simple if you use the formula. This is the way that you use the formula in your head, that, oh, it's going to be like that. Well, but if you use definition, let's look at how to use the definition here. Okay, I'm going to show you now. 21.1. If you want to use the definition, differentiate f with respect to x at the point xy. By definition, it is a limit f x plus h given comma y minus fxy over h, where h goes to 0. So basically, if you want to use the definition, this is a formal definition of partial derivative. It means you keep the second component fixed, and then you increase x to x plus h, where h goes to 0. And then you plug in that one. So you're going to get limit h go to 0. And then on the top one, you have fx plus y, fx plus h comma y. So this is going to be x plus h plus y squared. And then fxy going to be x plus y squared. So basically, I plug in x plus y, x plus h, comma y. I plug into this function, and then I put it here. Fxy is this function, so I put it here. And then you simplify the top one. So you're going to get x plus h minus x over h. And then that is the limit of h over h, and that is 1. This is how we use the definition. You can see that using definition is more complicated because you have to go back to limit and you have to compute limit from there. So it's your choice. You can use definition if you want, or you can use the formula if you want, but I'm gonna tell you that in practice using formula is a lot better. That makes sense. But if the question asks you to use the definition like this, you should be able to, right? Because it's just plug in the to the limit and then you compute limit, so you're gonna get the same answer. It's just, you know, longer solution. That's it. Okay, so let's do one more. 21.2. So if I want to do the partial derivative with respect to y, x, y here, so well, you know that the answer must be to y. Let's see why. So it's gonna be limit h go to 0. So the denominator gonna be h always. On the top one, you're gonna have keep x fixed, right? And then you increase your y. Keep x fixed, increase your y. And then it's here gonna be limit h go to 0. And then on the top, you're gonna have that one, which is x plus y plus h squared, right? And then now that thing gonna be x plus y squared. Okay, and then over h, and then that is going to be limit h go to 0. Well, you have to expand that thing, I guess, because it's like, okay, expand, what I mean is x cancel x, so you're gonna have y plus h squared first, and then minus y squared over h. So what is this limit? Well, now it's 0 over 0, so I have to do something. So, well, this is one-dimensional limit, so we're gonna expand that thing, so we get y squared plus 2yh plus h squared minus y squared. And then here you cancel out y squared, and then this is going to be limit 2yh plus h squared over h, and then limit h go to 0, and then you cancel one h, so you get 2y plus h. Well, once you plug in 0, so the answer is 2y. Okay, this is how you use the definition. You can see that even an easy function, this is not a hard function, this is an easy function, you still take 2 or 3 lines to do it. Well, how about this is xy e to the xy? Well, it's gonna be super terrible if you use definition, right? So definition is always harder to compute. You know, you already have a shortcut by using the formula, so I would recommend you to use the formula if possible. Does it make sense? Well, the purpose of this example, I put it in the slide because I want to show you how hard it is if you use definition. So this is why formula is also important in practice. Make sense? All right. Before I give you a break, so let's talk about the interpretation, and then I'll give you a break for 10 minutes. When we come back, we're gonna learn about 45 minutes more. Okay. Here, this is the last content for before the break. So we're gonna talk about the interpretations. So you know that in calculus 1, when you have a curve, derivative is gonna be slope of the tangent line, right? So the meaning of the derivative in calculus 1, it is a slope of the tangent line. Well, if you have the curve fx, and then the tangent line is the red one at the point AB, for example. So that means the slope of the tangent line is the f prime A. Oh, that is the meaning geometrically for derivative. How about partial derivative? Well, we define partial derivative with respect to x and partial derivative with respect to y. The meaning gonna be the same. Well, the partial derivative with respect to x, it is actually the slope of the tangent line, but it is the slope of the tangent line after you fix y to be constant. So basically the function of two variables, if you draw it, it's not going to be just a graph, it's going to be a surface. Once you have a surface here, if you fix one y, let's suppose that you fix y equal to 2. Well, you fix y already. So it means from the surface, you're going to have only the curve here. The curve here going to be, you know, the plane the curve that you cut it from the plane. And if you are looking at the slope of the tangent line that touch this curve, that thing is the partial derivative with respect to x. Does it make sense? Well, the same thing with the partial derivative with respect to y. If you fix one x, just fix it one x. So from the surface, you're going to have one curve. And if you are looking at the partial derivative with respect to y, it means you are looking at the slope of the tangent line that touch the curve. Well, let me show you the real example so you can see it a lot better. So let's suppose that you have a function fxy equal to 4 minus x squared minus 2y squared here. So if you use the computer to graph it, so let's suppose that we have a powerful computer or powerful software to compute it. You're gonna get the graph like this. This is the surface of 4 minus x squared minus 2y squared. This is the surface. You can try plug in this thing to Google, and then it's going to show you the graph of this function. It's going to be in 3 dimensions because you have a function of 2 variables. So you have x and y, and you have another axis called c. So for 2 variable function, you're going to need 3 dimensions to plot. So it's going to be 3 dimension here. The graph is, as you can see, in blue. And then when you take partial derivative with respect to x, it means you fix y. You can see that here I have a plane that I put the red line over there. Here, the plane that I cut the surface. This means I fix my y. So I fix one value of y. Here we can fix y equal to 1. We fix y equal to 1. So once we fix y equal to 1, so you use the plane y equal to 1 to cut it. And once you cut it, the thing that you get back, it's going to be the surface. The surface that I highlight in green here, this is the surface. Or not surface, sorry, the line, the curve. You get the curve here that I highlight in green. If you are looking at the specific curve that I highlight in green over there, and you looking at the tangent line to that curve, that is the meaning of partial derivative. So you're going to get the curve by fixing y equal to 1. And the tangent line here at the point A, B, C, gonna be the partial derivative with respect to x. Well, okay, as a BBTECH student, I know this is ridiculous that you have to learn the concept, but you know, maybe 5% of this class gonna understand what I just said. This is this is a geometric interpretation of partial derivative. Well, again, if you want to learn more, you want to dig into it more, you could take more math class after this class. But the purpose of this class, well, if you can compute partial derivative, you already get to the finish line of the course objective. Well, the idea here, if you know it, good, better. But if you don't understand, it's fine. Okay. The same thing with partial derivative with respect to y. You're gonna fix x, and then once you get the curve here, you can draw the tangent line. Make sense? This is why this is how we view the partial derivative with respect to x and y in terms of pictures. Why does it? I mean, why do we care? Why do we care the geometric interpretation? Well, as you know, in calculus 1, when you want to find maximum and minimum, you know, you want to find maximum and minimum in cal 1, you have fx, right? And then you take the first derivative, you set it equal to 0. And then you're gonna call x such that fx equal to 0, you're gonna call this thing critical value. Well, even you are pretty bad with calculus 1, you could remember this thing that in cal 1 you used to do something like you have fx, you differentiate one time, you set it equal to 0, you find critical value, and then that critical value is going to be your candidates for max and min, right? It's going to be x here, going to be your candidate that you could get max or min. This is in cal 1. So in cal 2, the same thing. So if you take the partial derivative with respect to x, you set it equal to 0. You take partial derivative with respect to y, you set it equal to 0. You're going to get the system of equation. Once you have the system of equations that you set both direction of partial derivative, equal to 0, you're gonna call the point xy critical point. So the point critical xy, the point xy that give you partial derivative equal to 0, gonna call critical point, and these gonna be your candidates for max and min for the surface. Like this picture, this is it look, if you graph this thing, it's gonna look like a cup. So the maximum gonna be here on the top. This is the maximum here. Well, the maximum here gonna be the point that the slope of the tangent line gonna be 0 on both way, x direction and y direction. So basically, the geometric interpretation gonna help us to develop the theory in terms of finding max and min. Okay, we're not going to learn that in this class. Okay, we are not going to learn how to find max and min in this class. It's beyond calculus. If you want to take this thing, you could take some class like I think for math people, they're gonna learn it in real analysis. So you're gonna, and some applications like application classes. So you're gonna learn it. But for calculus, I'm happy if you already know how to compute derivative. So, but keep in mind that we have applications too. So there are a lot of applications for partial derivative. One of them is you can find max and min by using partial derivative as well. But because of the time limit for this class, we don't have time to learn that thing, because it's gonna take about 2 or 3 weeks more to learn how to find critical point and find the max and min for function of two variables. Okay. Well, I mean, if you have calculus 3, we could put you to learn this thing in calculus 3, but you only have cal 1 and cal 2. All right, so let's take a 10-minute break now, and then when we come back at 11:02, so we're gonna talk about higher derivatives. So you could differentiate more than one times, as you've seen cal 1. So 10-minute break here, and then we come back. Well, let's come back at 11:03, and then we're gonna learn about 40 minutes more. Okay, here you can see that the plan that we have here. So we are now at March 30. So now today we learn partial derivative, and we're gonna learn higher order derivative more for today. And then well, I don't think we have time to do the chain rule today, but we're gonna come back, and next Monday we're gonna do the chain rule. And then for all applications, we're gonna put the clip for you, so you can watch it if you want. If you don't want to watch it, fine, because the content that I put on the Chakri day here will not be on the exam, so you don't have to be worried about it. So take your time if you have time, possibly after the final exam or anytime you want. If you want to dig into more applications or something, you can come back to this video, because I put it on the YouTube, so it's always there. And then not sure about the Songkran week here, if you want to have class, but well, let's chat later. But I feel like better to have class at April 11 here, and April 13 no class. Then we come back with integration, and wow, almost done. It's like super fast. Well, hope you enjoy the first year study of BBTECH. It's like, well, it is not a good timing yet for your generation because of the online thing, but hopefully in this coming August, they're gonna open the campus and you can come back to learn on site, hopefully. So I hope to, because I hate teaching online. So I would love to to teach on site too, and more chance that you're gonna see me again next semester, because as I told you at the first, I am I have to say that my specialty is statistics. So I like statistics. This is my area of expertise. So in the second year of BBTECH, you need to learn statistics, and there is a possible chance that you're going to see me again in statistics class. well, in this coming August. So, well, but it depends on your comment too. If you don't like to learn with me, you can comment it. You know, at the end of this semester, you have an evaluation form. If you like or if you don't like, you can tell. If you feel like, oh, Ajahn Monchai is so terrible, you put it in the comment, fine, and then, well, you know, next generation will not see me again because they're gonna kick me out, and then in statistics, maybe they're gonna change the instructor to someone else. So your feedback is always important to us. So if you like the style or if you want something, you can always give feedback. So we know that we have to improve and serve you the best, you know, because, well, if I don't get any harsh comment, maybe I'll see you again in statistics class next year, I guess. Yeah. But, well, hopefully it's going to be on site, everyone. We will see how it's going, and, well, Ajahn Tirapong, he already posted the midterm score, so it's already finished. So it means you have to take the best shot next for the final exam. So don't be scared about the low score. If you get low score on midterm, that's fine, as I told you. And 75 could be A. If you do pretty well on the final exam, well, if you, let's suppose that you get 30 or 50 on the midterm, and on the final you get like 46 or 47 or 50, or you do pretty well on the final. So I don't care about midterm, I'm going to give you A. It depends on, if you show me that you learn a lot and you take a big step, you improve a lot, why not? Well, let's give you an A. Why not? It's depends on instructor. So if you know that you already made a mistake on the midterm, well, let's change the way you learn and trying to improve yourself. Show me in the final that this is a new person, you learn already, you show your effort, and then, yeah, it will be fine. I monitor every time when you come into class, so I'm trying to learn the names of now, so I know who is in every day, and then I know who answer me a lot, who give me a participation. So this kind of person, I won't fail you for sure. So I know you attend class, you take a lot of effort. So yeah, how can I fail you? So that's the thing,นะครับ. All right, so wow, it's 11:07 already. So all right, so let's come back to the second hour class. So we're gonna learn about 40 minutes more, everyone. Sorry. So I thought that it's just only 11. So let's come back to the second hour class here. So the second hour class, we're gonna talk about higher derivative. So after you learn the first derivative already, so you feel like, Ajahn, in calculus 1, you can take more derivative, right? Like in Cal 1, when you take partial derivative with respect to, in Cal 1, when you have fx, you take derivative, or f prime x here. Well, Ajahn Ratinan taught you that you could do the second derivative. The idea is simple. You just take the result that you get, and then you do one more time. So it's gonna call f double prime x, right? We can do it in 2 dimensions too, but the harder way is, the harder thing is that because you have partial derivative with respect to x and partial derivative with respect to y, it means you're gonna have 4 ways to define second order derivative. Okay, this is called second partial derivative, or sometimes second order partial derivative. It's gonna be this notation. So let's look at the notation first. It's a little bit confusing, but you get better after you see this notation. So the first one is, well, if you have derivative with respect to x on the first term, you take x on the second term. The notation is going to be this one. If you have take with respect to x on the first term, and then the second time you take with respect to x again, the notation going to be this one. which means if you see this notation, the thing I circle here, it's gonna read it from left to right. If you see this notation, it's gonna read it from right to left. They are not the same, okay? So let's suppose that you have fxy here. This means you do f first on the first derivative. The second time you do with respect to y. So when you read it, it's gonna be fxy. You read it this way, left to right. So if you see this notation, this means you do x first because, well, this notation that I put the laser here, you're gonna do right to left. So you have to do x first and then y. Because the order gonna be you do something in parentheses first and then you do the outside one. So be careful with the notation because fxy and fyx, they are not the same. This means you do x first and then you do y. This means you do y first and then you do x. Even most function, they're gonna give you the same answer for fxy, fyx. I understand it, you know, like most of the time when you compute fxy and fyx, they're gonna give you the same thing almost every time. But they're gonna be only some function that give you different things. But the polynomial function, the trigonometric function, all continuous function that you know, the simple one, gonna give you the same one. Well, that is not a coincidence. There is a theory behind it, but most of the time it's gonna give you the same thing, but its meaning they are different. So fxy you do x first and then you do y. Fyx you do y first and then you do x. Okay. So fyy this is easy because you do y 2 times. All right. So let's look at example here. Let's try to find the second partial derivative of this function. Okay, let's do it. When the question says something like this, you have to do all of it. Okay, let's do it. So first one I'm gonna do, well, let's take a look at the function first. This is actually, the yellow one is actually constant. When you take derivative, it's gonna be fine. It's gonna go away. But the term that I highlight in red over there need more work. Okay, so let's do something first. Well, we're gonna take derivative with respect to x first, okay? Well, when you take derivative with respect to x, what would you get? So you're gonna see that the first term here, y e to the xy. So you take derivative with respect to x, which means y is constant. So y is constant. You take derivative e to the xy. So you're gonna get e to the xy. But by the chain rule, you're gonna have y with you. Make sense? And faster than before, right? So y is a constant, keep y, and then e to the xy, you get e to the xy. And then because xy is an inner function, you differentiate xy with respect to x, so you get y. And then the second term here, x cubed times y squared. Y is constant, so 3x squared times y squared. So keep y squared over there. X cubed gonna be 3x squared because I take a derivative with respect to x. And then the last one is 0. So you simplify it, so you're gonna get y squared e to the xy plus 3x squared y squared. This is the first the derivative with respect to x. Okay, and from here you can compute f double prime x. I should say derivative with respect to x 2 times. So which means you take the thing that you have in the box here, do derivative one more time. So it's gonna be y squared, and then e to the xy, you're gonna get e to the xy y again, right? Because y squared is constant now, so constant. E to the xy here, this is e to the xy times y, because use the chain rule. And then the last term is gonna be differentiate with respect to x, so you get 6x times y squared. Am I right? And then, well, which means at the end, so your answer here gonna be y cubed e to the xy, and then plus 6xy squared. Well, this is the first answer, fx differentiate with respect to x 2 times. Well, you also need to compute fxy here. Well, fxy here means you take the thing that you have in the box here, the purple box, you differentiate with respect to y. Well, this time it's going to be a lot more complicated because this term that you have y squared times e to the xy, you have to use product rule, right? The second term is easy, but the first term is like you need to use a product rule. So it's going to be y squared, and then differentiate e to the xy, you get e to the xy times x, product rule, nah? And then plus e to the xy and then 2y. And then the next term, 3xy squared, you use the product rule. Not product rule, x is like constant, so you leave it there, and then you only differentiate y squared, so you get 2y. So I know this is a bit fast, but this term I differentiate, so I get that. But the hard thing is the first one. So y squared, I keep it, so right, and then I differentiate with respect to y, so I get that for e to the xy. So I get e to the xy times x, and then e to the xy here, and differentiate that, you get 2y. Simplify it, so you get the answer. So this is xy squared e to the xy plus 2y e to the xy, and then plus 6x squared y. Well, this is the second answer. Make sense? Well, I hope it does make sense for you. It is not that terrible, this question. All right, so that's the first one. The second one, I can differentiate with respect to y first. So let's go back to the original function here. If you want to differentiate with respect to y, what happened? So, well, we have to use product rule. So it's going to be, let's take a look at the original function, okay? So, well, the first term we have to use product rule. It's going to be y e to the xy times x, and then plus e to the xy times 1. Well, what happened here is I have y e to the xy. I want to differentiate with respect to y, so I keep y. I differentiate the second term by the chain rule, I get that, and then I keep e to the xy. I differentiate y, I get 1. Okay, it product rule, just product rule. And then here, this is x cubed y squared, right? So that's mean gonna be x cubed, and then y squared differentiate, you get 2y, and that the last one is 0. Okay. Simplify it. So we get xy e to the xy plus e to the xy plus 2x cubed times y. Hard, yeah, a little bit hard because so many terms that you have to differentiate. Okay. Well, let's do that. Well, fyy first, okay, everyone. Differentiate with respect to y one more time. So this is going to be you have to use product rule again for the first term. Keep x here, x here, keep it here because this is a constant. So here y e to the xy, you can take a derivative by using the product rule. So you're gonna get y e to the xy times x, right? And then plus e to the xy times 1. So here, y e to the xy, I use a product rule, so I get that. Together with the chain rule inside. And then e to the xy, I differentiate, so I get e to the xy times x. All right, and the last one, I get 2x cubed. Well, you know, you don't have to go fast like me. Some of you can say, Ajahn went pretty fast. Well, you don't have to. Well, if you feel like you want to take slow step by yourself, fine. So when you do it at home, you don't have to go faster like me. Because some of you like to take more time, totally fine. Because if you are a beginner, it's going to take time for you to do it, you know. And then I multiply the thing, so you get x squared times y e to the xy, and then plus x e to the xy. Well, I have x e to the xy 2 times, so I have 2 here, or 2x cubed. All right, I get the third answer here. This is fyy. Okay. All right, last one, fyx. Well, actually, fyx, well, after we compute, you're going to see some observations after you compute it. So let's do it. So we have fy here. You think that I box in green. And then I'm going to do derivative with respect to x. With respect to x. So y is constant. So take y out. So y here is constant. So it means I need x, I need e to the xy, and then which means you know I have y here, I have x e to the xy, so I get I need product rule, right? I need product rule, so it's gonna be x e to the xy times y, and then plus e to the xy times 1. Am I right? Yeah, because one more time now. I pull out y here. I put a y here, which is y here, okay? And then I have x e to the xy inside. Let's look at just this term now. X e to the xy. X e to the xy. So when I differentiate, I get x e to the xy times y. And then plus e to the xy. And then x here, I differentiate, I get 1, okay? And then after that, I have e to the xy times y. Because this term, I have e to the xy times y. And the last one is the polynomial is always easy, plus 2y times 3x squared. Well, if you simplify it, so you're gonna get, well, let me cheat. So if you simplify it, so you're gonna get xy squared e to the xy, and then plus e to the xy, and oh sorry, 2y e to the xy, sorry. 2y e to the xy, and then plus 6x squared y. This is also an answer. Okay. From this step to this step, just simplify it. So the first term is here. The second term multiply y is here. And this multiply this and this gonna group together, so you get this thing. And then the last one is that. So you simplify, so you get the answer that I box it. So you can see that what I want to show you is, you can see that fxy and fyx, they give you the same thing. See that? Give you the same thing. This is not a coincidence. We have a Carroll theorem said that fxy and fyx going to be equal to each other if the second order derivative exists. Well, so this is the first example. So I show you how to compute the second order derivative, the second order partial derivative. But when you do it, so you can skip this part. You can do this, this, and this, and you can claim that fyx going to be equal to fxy as long as you apply the Carroll theorem, which we are going to see in the next slide. Sounds good? Well, if you cannot jot down this thing now, so we're gonna post a clip after for you. Well, some of you have a question in the chat already that how do I compute fyx here? So fyx, I start from f here, and then I take the first derivative with respect to y, so I get something in the box here. And then I take something in the box here, differentiate with respect to x again, which means now I'm going to keep y constant, which means you can see that I put out y here because the first term here, y is constant. So I pull out y immediately. And then have x e to the xy, which I have this by using the product rule. Okay. Something like, yeah, I have e to the xy here, y is constant. So it's going to be e to the xy times y. Okay. Because I differentiate with respect to x, y constant, yes. Okay. All right, so this is the Carroll theorem that I just told you before, that, if you have function f defined on a disk D that contain the point A, B, so you need a neighborhood that contains the point A, B. If the function f, x, y, and fyx are both continuous on D, then fxy and fyx, they are equal to each other, which means as long as you know that the second derivative exists and they are both continuous, so they are equal to each other. This is a good result from Carroll theorem because, well, it's tell me that and tell everyone that, well, if you have compute fxy already, and if your function is good enough means the second order derivative that you compute, they are actually continuous. They're gonna be the thing that they are equal to each other, which, you know, the function that we learned in class, polynomial, trigonometric function, logarithm function, exponential function, they are all continuous, which means this one always hold for the function that we learn in class. Does it make sense? The function that we learn in class, like polynomial, trigonometric function, anything that you see beforehand from Cal 1, they are all continuous, which means this is going to be fine. Because you don't learn something hard like fx equal to 1, where x is a rational thing, and it's going to be 0, where x is irrational. So they're going to be harder function that the function is not continuous. For those type of function, this thing will not work. But for you, at your level, you only learn polynomial, trigonometric function, logarithm function, and exponential function. They are continuous. So fxy and fyx, you can claim that they are equal to each other. Fine. Okay. So again, when you see second partial derivative here, now you can reduce your word. Let's do just fxx, fxy, and fyy. Because we know that this gonna be the same thing with that. Because the function is continuous. When you take derivative, the derivative gonna be continuous too. Okay. All right. So let me see what we have time. Okay. Oh, wow. Perfect timing, because this is a lot example for this slide, and then at the, well, we're gonna end the class by completing this slide. Okay. Perfect, because I think I need 10 to 15 minutes more to complete this one, and then we can go and have a good lunch. All right, so let's look at example 23 here. Any question, everyone? Anyone? Okay, let me see the chat. Okay, no question yet. All right, so let's look at the last one together. So let's practice more. So let's suppose, well, this function now is easy. So fxy equal to x cubed times y squared minus x squared sine y minus cosine y. I want you to evaluate the following quantities. So first of all, I want you to do 23.1. We're gonna take the second order derivative here. This notation. So you have to do x first, remember? This notation means you do x first and then you do y, because it's gonna go from right to left. This notation is gonna go left to right. So which means you're gonna do x first and then you do y. Okay. So first of all, you're gonna take the derivative with respect to x first. So what would you get? So the first term, take derivative with respect to x. So you get 3x squared times y squared. And then the second term here, x squared sine y, what would you get? So you get 2x times sine y. The last term, cosine y, so 0. Because here, when you take derivative with respect to x, constant. You can see that all I care is just I differentiate x term. This is constant, and this is constant. So that is what I get here. If you want to simplify, so you're gonna get that negative 2x sine y. Wow, I like it. It's pretty simple. Yeah, so no product rule, no quotient rule. I like it a lot. And then you can take one more derivative. So derivative with respect to y. Okay, take one more derivative outside. So which means you're gonna take derivative with respect to y of this function. All right, and then that's gonna be what? It's gonna be what? Got it's going to be 3x squared, keep it. And then y squared going to be 2y, and then 2x, and then differentiate side, you get cosine. Pretty simple. So the answer is going to be 6x squared y minus 2x cosine y. And then after that, you evaluate, well, this is a notation, curl square f by curl y curl x. Well, this is the same notation. This and this, it's just the way you abbreviate it. And then this is going to be evaluate at x, y equal to 1 and pi over 3. Well, this is going to be 6 times 1 square times pi over 3. And then minus 2x cosine pi over 3. Okay, 6 times pi over 3 is going to be 2 pi. And then x is 1 already. X is 1. So 2 times cosine pi over 3. Cosine pi over 3 is 1/2, right? That means this is 1. So the answer is 2 pi minus 1. Okay, simple. All right, last example for today. So example 23.2. Well, in the meantime, any question with 23.1? Hit the reaction if you understand it. The crab one, the thumbs up, the hard one, or the sad face, or anything. Good. All right, I want to see how many people understand it. Okay, thank you. Okay. All right, so hope you understand it now, because it will be on the exam now, this type of question. So 23.2, so let's look at that. So this time I'm gonna do derivative with respect to x 2 times. Okay, so I'm gonna do fx first. Oh, this is, I copy from the left one, right? Because they are the same thing. So this is take derivative with respect to f. Take derivative with respect to x. So I have that. Now we do one more time. Okay. So this term you do with respect to x. So you keep 3y squared, and then you do 2x, right? And then this thing you have sine y and 2x here. So it means you're gonna say that you're gonna say that 2 sine y gonna be your constant, right? And then differentiate x, you get 1. Okay, so it's 6xy squared, and then minus 2 sine y. Okay, this is f(x). Wow, this is pretty simple, isn't it? Let me check with my answer. Is that correct? Hold on. Where is my answer? Yeah, it is correct. Yeah, simple, that's simple. All right, so fxx times evaluate at 1 and pi over 4 here. So you're gonna get 6 times 1 times pi over 4 square. Well, you can see that what I use is radian, right? So I don't care about pi. You know, some of you are gonna get confused when you see pi over 4 here. Well, this is just a number, so treat it as a number. So don't be scared with the notation pi here. Pi is just a number. So here this is 6 times pi square over 16, and then minus 2 times sine pi over 4. Sine pi over 4 is square root 2 over 2. And then that is, okay, let's cancel a little bit. So that is 3 pi square over 8 minus square root 2. Okay. All right, that's correct. That is the answer for this question. So this type of question, I hope everyone can do it, because it's not hard at all. And yeah, this type of question, this is the one that I'm gonna ask on the exam, I guess. So make sure that everyone know how to differentiate 2 times. You know, the notation gonna be a little bit odd, as I told you that one form of notation they go left to right, another form they go right to left. So make sure you notice the difference here. So if you want to practice on partial derivative, you have practice problem here. Example 24, 25, 26, and 27. So you can have that and then find partial derivative. You have that and find partial derivative. Well, number 26 and number 27, these are the tough one. I mean, not 27. 26 are the tough one because it's gonna prove things. I would say these two examples, they are optional. If you don't want to do it, fine. But if you want to do it, it's good to do it. It's gonna take some time for you to take partial derivative of this thing 2 times, and then you have to simplify a lot, because if you simplify everything and then you make it to be this quantity, it's gonna add up to 0 perfectly. This question is not hard, but just tedious. It's just tedious. So it's long and tedious. So if you have more time, you can do it. But well, I believe that if you can do 24 and 25, you are done with this second order derivative, because the concept is easy. Number 27, this is the practice one, that if you want to practice using the definition of derivatives. Okay, they are optional, you know. I don't think we're gonna cover this thing on the exam, but it's good practice if you want to do it. But I think this year we're gonna skip this part on the exam. So the exam gonna ask only the simple thing, because I don't wanna, you know, put your score to be very low, because you know you already get low score on the first half of the class. So the second half, I want to make the exam to be a little more relaxed and easy for this part. Okay, so optional things for on example 26 and 27. Okay, well, we end the partial derivative lecture now. Well, next Monday we're gonna talk about the chain rule in 2 dimensions. So that is going to be let me tell you 3 or 4 more minutes here before we leave. So next Monday we're gonna do the chain rule now, everyone. So let's come back to do the chain rule. Okay, and that will be the end of derivative part. The thing that we're gonna cover in the live class. And then, well, you know, application is gonna be on the video, as I told you. And then when we come back the following Monday, which is going to be April 11, it's gonna be a Songkran week, but you know, we have Monday and Tuesday as, you know, a regular day, not a holiday. So we're gonna learn a little bit on integral, and then we come back after Songkran with 4 more class on double integral, and that's all.